Hi there, I'm Alberto Gutierrez and this is the Practical Actuary channel. This is part 2 of the series GLMs with gradient boosting machines. In part 1, I provided a conceptual overview of gradient boosting machines. And given those concepts, how one can then construct a GLM with gradient boosting trees. So part 2, which is this video, I go over how one can implement GLMs with gradient boosting trees in Python. So let's go ahead. Okay, so before we begin, just to provide you with an overview of the Python libraries that I'm using. I'm using the H2O package, and this package I'm using to build a GLM model. And then I use the XGBoost package to build a GBM. Also for comparisons, I'm building a neural network as well as a combined natural neural net, just to compare the performance between the two techniques, being boosting GLMs with trees and a combined natural neural net, which is boosting GLMs with a neural net. Okay, so let's dive in. So essentially then, the data that we are using is the French dataset. And this is the frequency dataset, right? So it's predicting the third-party liability claims. And yeah, so this is available, this is an open data source. Yeah, I got this data from Kaggle site, but you can find it in many places. Okay, so I love using this package, SweetViz. So what SweetViz does is it provides a nice report. It profiles the data for you. So you can essentially just have a look at your data, such as the associations between the variables. Are there any missing variables? Kind of what is your distribution of the variables? I won't go over this right now, but it's important that before actually going into modeling that you understand your data. So having that said, I will essentially assume that the data is already prepared and fit for modeling. Okay, so we continue. In this case, it's essentially creating the basics. So I've got my list of features, so my list of variables that I'm going to use for modeling. My weight, which is the exposure, so that's the time at which the specific policy is on risk, and then the target being the number of claims. Okay, and then from there I essentially split my dataset into a training and test dataset, where my training dataset is 80% of the records and my training is 20% of the record. Okay, and these are my dimensions after splitting them, and now we're ready for modeling. In this case, I'll be fitting 6 models, right? One is the null model or homogeneous model, which is essentially the weighted average of my response. The second, I'll be fitting a GLM. Then I'll be fitting a GBM, so normal gradient boosting machine. Then I'll be fitting a GLM with GBM, so it's boosting with a GBM with trees. Then I'll be fitting a neural net. In this case, it's a ResNet implementation. So ResNet is kind of like it is boosting in a way, but within the neural network. And then finally, I'll be fitting a combined natural neural net, which is basically boosting a GLM with this neural net being a ResNet. So those are the models that I'll be building, and then at the end we'll just compare the performance of the models. So as noted, the null model is essentially the weighted average, so that's the average prediction. And yeah, it's as easy as that. And then a GLM, I'm using the H2O package. I mean, you can use other packages. I just like the H2O. So I initiate my server, my local server, and then I begin essentially converting a data frame into an H2O frame. ensuring that my data set is within the H2O frame so that it is fit for modeling. I then fit a GLM with the person being the family, and it's a log link. I set my lambda to be 0, which means that there's no regularization, no penalties being applied on my GLM, so this is a pure GLM. And then I set my offset column, right, which is essentially the log of the weights. And I provide both my training and validation set, my columns as well as my target, and I fit the model. So together with the data preparation, that took about 14.4 seconds to fit. And then these are the outputs of the GLM. Skip this. And then essentially building my prediction function. And then essentially having my predicted values into a GLM prediction column. So I'll have prediction values for each model so that I can then essentially those values will be used for performance comparisons later on. Okay, but also this will also be used with my GLM boosting with GBMs. As you know, that technique as well as the combinatorial technique requires that a GLM is fitted first, right? A good GLM is fitted first, and then those become then offsets in those models. Okay, after fitting a GLM, I then fit a GBM using the XGBoost package. So in my XGBoost, I have to prepare data, right? So convert a pandas data frame into a D matrix data frame. Right? So this is a kind of data frame that is fit for the gradient boosting machine in the XGBoost implementation. But what's important there is, so obviously I set my features, my labels. I ensure that I'm enabling categorical features. So that means that my model can train on categorical features and not just numerical features. And then I set my base margin, and this base margin is the log of the weights. So think of this as an offset, right? Like in the GLM case. So in the GLM, my offset is my log of weights, and this is the same, right? Where I set my base margin. So base margin is very similar to an offset. So that's my log of weights. Okay, then I pre-process my data so that both my training and test data set is converted to a D matrix. And then I set my parameters for training. So the objective here is the count person. So this ensures that, suppose the loss function associated with that is similar to like a person deviance loss function in the GLM. And by default, I believe this is a log link function at the end, right? So it's the model structure is pretty much similar to a GLM, except instead of a linear function of the product of the parameters and the predictor function, this is a linear function of weak learners. Okay, so then I set my max depth to 6, so my trees can only go 6 levels down. So this eta is a learning rate. Subsample, I believe this is sampling my rows, to basically be 80% of that, and then by tree, I'm sampling my columns, so I'm randomly selecting 80% of my columns for each tree. And yeah, so those are essentially my parameters. Okay, then I train it where my maximum number of rounds is 200, so I can only have, call it 200 weak learners max. But then I, set early stopping rounds to be 10. So if there's no improvement in my model, then it's, after 10 rounds, then it stops my model. And that is basically my best model. And this ensures that I'm not overfitting the data, where it essentially looks at the validation score, right? The validation loss. So if this essentially starts to deteriorate, where there's no improvement essentially after 10 rounds, then it stops there. Okay, so this is how it looks. Each round, as you can see, the negative log likelihood, the percent negative log likelihood is reducing for both the training and the validation set. And I think it stops at around 80. Where, as you can see here, there isn't any further improvement in the validation loss since then. So that is the lowest, but it's kind of like hovering at around this level without any improvement to the model, whereas in the training set will continue to reduce, but your validation won't reduce. So it's at that point in time where you sort of need to stop your model, just to ensure that you don't overfit your training data set such that it becomes quite poor when you apply it on unseen data such as your validation data set. Okay, then essentially building my prediction functions, and then I get the predicted values from my model, which I will use much later on. Okay, now it's time to build a GLM with a GBM, so boosting with a GBM. It's basically the same as GBM, right? Where the only difference now is that I set my base margin. So remember, base margin is similar to an offset. My base margin in this case is the log of my GLM prediction. This GLM prediction is essentially predictions from the model that we built just before, and yeah, that's all that is required. Essentially everything else looks the same as the normal GBM. It's just purely just setting that base margin to be the GLM prediction. Okay, so everything else remains the same, and then these are the results. So as you can see, it stops up after around 111, and then we continue. This is our prediction function, and then we get the predicted values from that model. Okay, and then now it's time to build a neural net. Okay, so neural net, this is my custom data model. It's basically pre-preparation, right, for my neural net. The most important essentially is that all my categorical variables, right, I essentially apply a one-hot encoding to those categorical variables, and then all my numerical variables will go through a standard scalar, which I'm basically applying some sort of normalization using a standard scalar. So a standard scalar saying whatever the value minus the mean divided by the standard deviation. So that's the standard scalar. So those are the transformations that I'm making to my data set, and then that is basically applied to both my training data set as well as my validation data set. Okay, so I am using PyTorch to build my neural net. And I'm using Lightning PyTorch, which is kind of like a wrapper on top of PyTorch to basically make my data more clean. Okay, so we carry on, and this is where I now define my combinatorial model. So first I need to define or basically create a function which calculates the percent deviance loss. So in this case, that is the formula for percent deviance loss. I also have to define an exponential activation function, and this is how I define it. And because I'm implementing a ResNet implementation, right, so I have to define my res block. And the res block is essentially consisting of, so I first take the x value, and in the x value, I am, making a copy of that, right? And I'm passing through a ReLU function on top of my linear. So it's a linear layer, and then applying a ReLU on top of the linear, and then there's a dropout, and then also apply the same linear on top of it, and then a ReLU, which is the out plus my residual. So this is my implementation of the res block, and I'll essentially be then stacking these res blocks on top of each other. But yeah, this is my implementation of the res block, right? And it's basically size of the input dimension. So after my pre-preparation, my pre-processing, I'll have a number of columns, which will include some one hot encoding column. So however number of that columns as a result then becomes sort of my width of my res block. Okay, once I've defined these key functions or these key classes, so Poisson deviance, exponential activation function, and the res block, now I can build my neural net. And my neural net is essentially a sequence of my res blocks. So in this case, I'm stacking 10 blocks, 10 res blocks on top of each other. And then my second last layer here is a simple linear layer, which essentially then, where the output is a single neuron. And then I apply an exponential activation function on top of that neuron. Yeah, and then my forward is essentially that, but then I also multiply by, in this case it's the offset, right? It's the weight, it's the offset. If the previous prediction is not set up, is not defined, then it takes the weight. So this p here is the offset. So it just multiplies by the offset, right? Okay, then I define my training step and my validation step. So this is just to ensure that I'm logging, or rather I'm using the Poisson deviance loss function there to calculate the loss, and essentially then logging the training loss as well as the validation loss. Then I'm using the n-Adam optimizer, and this is my training model function. So in this case, I seed everything, right? So this is just to make sure that I'm able to reproduce my model, my neural net model. So as you know, there's a number of stochastic processes in here. So it's the randomization of my batches, from my training data set. It's the randomization of my initial weights. And yeah, it's just to ensure that there's a seed on all the stochastic processes, so that I'm able to produce the exact same results if I rerun this. Okay, so I then instantiate my model, my CAN model, set my early stopping parameters to ensure that I only wait for 5 rounds to check if there isn't any further improvement, and then I take the best model. Yeah, so deterministic equals true. So this is just to ensure that everything is essentially deterministic. There's no stochastic processes, right? So it's setting a seed, ensuring that I get to the same result. Okay, then I fit my model, and that's basically my training function. Okay, now it's time to train a neural net model. So this is with the ResNet implementation. And yeah, it's as simple as that. So this model took about 1 minute and 52 seconds to build, and it stopped at a validation loss, in the last epoch of 0.306. Okay, then we build our prediction functions and we get our predicted values. Right, now it's time to build a combined actual neural net, which is then essentially setting that offset, which is the prior prediction, to be a GLM prediction. And it's as simple as that, because that's how I build my model. And yeah, so then this one took about 1 minute and 59 seconds. And as you can see, the last epoch had a validation score of 0.304. Okay, then build my prediction function and I get my prediction values, predicted values. Now it's time to evaluate my models. So in this case, I'm using deviance. This is the Poisson deviance and my Gini coefficient, right? So I want my deviance to be as low as possible and my Gini coefficient to be as high as possible, right? So it means that the lowest Gini coefficient means that I'm predicting the values accurately. The higher Gini coefficient means that I'm differentiating as much as possible, right? I'm able to differentiate those instances which has very low frequency compared to those that have very high frequency. Okay, so that's what I do for all the models. And these are my functions to calculate my Gini coefficient. And then my Poisson deviance, I'm simply taking that from the model diagnostics package. It's a very good package. And yeah, so I just iterate over every model and basically calculate the Poisson deviance, the average response, and then the predicted. So it's good to compare the two to see if there's any bias. Likewise with the total as opposed to an average, and then my Gini coefficient. Okay, so these are the results of my models. So I think we need to compare against the null prediction, right? So as you know, GLM does perform better than the null with the result of 0.3088 from a Poisson deviance perspective, and it does pretty well where there isn't really much bias from an overall perspective, from a global perspective. And then a Gini coefficient is quite good at 0.42. So this is my standard GLM. Now with my XGBoost model, a GBM, it does fantastically well on my Poisson deviance at 0.3001. I think it also does quite well, so there's not much bias to the model, and it does exceptionally well in the Gini coefficient, beating GLM, right, whilst maintaining very great Poisson deviance there. Okay, then my GLM with the GBM, so this is GLM with boosted trees. So it performs slightly worse than normal GBM model, but definitely better. So it's quite close there. The bias tends to be quite good, and it's pretty on par with the Gini coefficient. I would say it's kind of on par with a novel GBM model. So I suppose here the benefits that you get here is you maintain the same predictive power as a normal GBM model, gradient boosted trees model, but what you do get is separate components where you have your GLM component, which is much more interpretable. You can implement whatever constraints, and then you have the gradient boosting tree component, right? The boosting component, which essentially takes care of the complex nonlinear and complex interactions between the variables. So I suppose it gives you that advantage. And likewise for a neural net, so this is the ResNet, definitely performs better than GLM, but not as good as the gradient boosting machines. For both, I suppose, the Poisson deviance as well as the Gini coefficient. Okay, and then the combined actual net does better than the normal combined, the normal neural net, so the ResNet, but does not perform as well as the gradient boosting machine models. However, it is kind of on par from a Gini coefficient, so it's able to differentiate quite well, but from a predictive power, not as great as the GBM. It is quite good, just not as great as the gradient boosting machine. And yeah, seems to be, there seems to be quite a bias, maybe not that much, but there's definitely a bias. I've noticed that neural networks tend to be quite sensitive from a bias perspective, in terms of from round to round, right, from epoch to epoch. So definitely some some investigations in terms of when the model should stop, so that it is not as sensitive from epoch to epoch, in terms of ensuring that the model doesn't have bias. Okay, so yeah, that's the overall performance comparison. We can then look at reliability plots. So reliability plots is essentially splitting your data sets in terms of prediction. So maybe you can split in terms of like, okay, within the first 5% claim frequency, then the next 5% claim frequency, so it's between 5 and 10, and between 10 and 15, etc., etc. So you can choose your bins, and then based on each bin, you calculate what is the average prediction, and then in that same what's called the same records, you then also calculate your average actuals, right? Your average actuals, right? And they should roughly be the same. And if they're roughly the same, so it's basically what you'd find is that they would go on the 45-degree line here. So if they are the same, which means that the model is quite reliable. Right? If it's over or if it's under, then it's not as reliable. It's either under predicting or over predicting. So yeah, just it's a good way to diagnose your model. So in this case, most of the models are quite reliable. I suppose then you do have the extremes here, where you can get quite wild predictions. So it's a good test to see whether your predictions are quite consistent in the extreme values. Okay, and then this is plotting the bias or model bias plots. So all the models seem to perform well, seem to not have any bias, with the exception of the combined actual neural net, as I told you, that there was some kind of a bias there. Okay, and then you can do the same thing by feature, right, for each feature level. So I won't go through this in detail, but yeah, that is good. And then some marginal partial dependency plots. This will obviously compute marginals unless you set a prediction function, which will then compute the partial dependency plots. These tend to run quite long, so it's just simple marginals, and the marginals here, I suppose, is just simply the average of the predictions, within the levels. Okay, yeah, I believe that's what it is. Yeah, I think that's what it is. Okay, then you can look at the marginal plots. Yeah, for each of them, right? So they all, tend to be quite good. But you can look at each variable and see which model tends to be better than the other model. Yeah, so I won't go through this in detail, but it's a useful package, plots, just to analyze where your models might be predicting well, or over predicting or under predicting. Cool. And now we can actually analyze the GBM boosting component. So in part one, I showed what a GLM with a gradient boosting machine looks like. So if you think about the linear predictor space, you have your GLM component, which is a linear function of product of your parameters and your variables, plus then the GBM boosting component, which is the linear function of your weak learners. So because they're in a linear predictor space, right, and in this case the length function is a log length function, what you can do is then apply the inverse log length, which is the exponent of that, and because of that you can then separate out multiplicatively the boosting component, and that becomes your relativity, right, coming out of your GBM boosting component, right? So if it's over 1, it means that your model is suggesting a higher predicted value compared to a normal GLM. If it's under 1, then likewise it's a lower prediction than your GLM. Then if it's 0 or very close to 0, then there isn't really much difference between the GLM with the GBM and the GLM. Okay, so that boosting component should ideally would, I suppose, be centered around 1, could be less than 1, could be slightly more than 1, but it should be centered around 1, but definitely greater than 0, and could be up to infinity, right? But in this case it is between 0 and at a max 5, right? But they're mostly weighted here between, call it a 0.5 and a 1.5, right? And yeah, I mean, you can apply constraints here to basically say, well, I want to stop at 1.5 and start at 0.5 if you don't want much differentiation beyond those points. But this is how the boosting component looks like. You do have majority of your records being below 1. That's about 61%. And then the remaining 37% essentially is above 1. Okay, now given that we can then compare the distributions, right, between these two subsets, okay, and essentially we're gonna do an AVE comparison, right? So we can use area. So let's go to area, right? And in each area, right, I'm essentially plotting where the boosting component, right, this is the green bars and the green lines, is less than 1. Right, it's less than 1. And if it's less than 1, my GLM AVE, so this is my actuals divided by my predicted value, so the actual versus expected, is less than 1, right? But my GLM with the boosting model tends to be around 1, so we want it to be 1. And then likewise, where the boosting component is greater than 1, we see our GLM AVE at around 1.2, kind of higher there, whereas in our GLM with boosting essentially is at around, and this is what we want, right? We want our models to be AVEs to be just roughly around 1. There will be some some randomness, some random processes in place, but it should average around 1. And yeah, so this shows that for those, subset of the data, our GLM with boosting essentially does quite well. And yeah, and you can then compare the different distributions, right? So let's choose driver age. Yeah, we can choose driver age. It's loading, so you can see the distribution, right? So the GLM is picking that the younger drivers, right? Some of the younger drivers, compared to the GLM, would require a further discount or further reduction in the predicted values compared to GLM. And the opposite is true for the older drivers. Now this is how the distribution looks like between the two. And if I zoom into the AVEs, you will see that the AVEs of my GLM with boosting tends to average around 1. Now, whereas in my GLM AVEs tend to be deviating from 1, which then again shows that our GLM with boosting does quite well there. Okay, then you can do the marginal plots on the boosting component values just to see average where it tends to apply a higher predicted value or lower predicted value. The relativity is above 1 or less than 1. So it's good plots just to understand what the boosting component is doing. Of course, these are complex interactions and nonlinear relationships, and it becomes very difficult to visualize that. But these are some of the techniques that you can use to basically analyze the boosting component, which consists of complex interactions and nonlinear relationships. Okay, so that is it. I will be pushing this notebook into the GitHub page, so I will provide a link to the GitHub repository where you can find this notebook. And yeah, until next time.